Greetings, everyone. Welcome for last session of Drilling Fluids Facts Practical Approach. We did before 3 sessions. Session number 1 was introduction. Session number 2 was Bud Engineers Day Approach. Session number 3 was operational concern. And this session, inshallah, will be about inhibition and contaminations. Agenda for this session will be inhibition mechanism and contaminations, and as usual, at the last of the session will be question and answers. Inhibition as a definition is a prevention, arrest, or slowing the hydration, swelling, and integration of clays and shales. Prevention, arrest, or slowing the hydration, swelling, and disintegration of clays and shells. Shells stability generally obtained in water-based mud from many mechanisms such as ionic inhibition, encapsulation, and physical plugging. The degree of stability in water-based mud is not be as great as with OBM, but proper treated water-based mud can be used successfully and drill the troublesome shells without any problem if just we treat it properly and our properties was as programmed. We have many inhibition mechanisms. The first one of inhibition mechanism here to drill with non-aqueous phase or with non-aqueous mud. Here, non-aqueous mud, we mean OBM, oil-based mud, or synthetic based mud. Synthetic based mud is same as OBM. It's just the difference here. OBM is base fluid is a diesel. Synthetic base mud is base fluid is another oil. It's not diesel. It's sulfur oil or non-hydrocarbons oil, but it's considered same as OBM. Here, the first inhibition mechanism, no water will touch the formation, so we'll prevent swelling from the beginning. No water will go to touch the formation and let the formation swell. Because in OBM, we know the water will be the internal phase, will not be as external phase. So will not touch the formation. The second mechanism of inhibition, here we said reduce the pH. Reduce pH, just we are meaning avoid adding chemical which disperse the clay, such as caustic soda. If we add caustic soda, so caustic soda will disperse the clay, and this will work against the inhibition because we need to inhibit the clay from dispersion. But we don't have type of mud, is just rely on reducing pH as an inhibition mechanism. But this is one of mechanism, but we don't have type of mud, just only reducing pH to provide inhibition mechanism. The third mechanism here is the dehydration. Dehydration increase chloride content, increase salinity. So we will work by osmosis, because when we increase the salinity of the mud or increase chloride content in the mud, so by osmosis the water will go from low salinity to high salinity by osmotic. So this will make dehydration for clay. The poor water in the clay will go from the clay to the mud by difference in osmotic. This is dehydration. If we have low salinity in our mud, that will lead to water phase in our mud going to formation and make swelling. The fourth mechanism of inhibition is ionic inhibition. Ionic inhibition or cation exchange. Here we talk about the two cations, potassium and ammonium. And potassium here will, or ammonium will replace the sodium inside the clay layers and prevent more water going. We will discuss in details about the cation exchange. Next slide. The mechanism number 5 and number 6 is a physical plugging and encapsulation. Physical plugging, here we have two types for physical plugging. It's silicate by precipitation is a make also the physical plugging, or polyamine. It's in MI called color stop. This is the trade name, but this is as a chemical name is a polyamine. Polyamine is also provide physical plugging and reducing fluid loss, and this also is a mechanism of inhibition. The last one here, encapsulation. This is by BHBA or glycol. Glycol is a provide coating, also meaning of encapsulation, and BHBA is provide encapsulation for shale. Ionic inhibition, this is, here we'll talk in details. Potassium or ammonium cations enter between the clay layers. We know the clay, his layers, and in between layers we have sodium atom. This is montmorillonite clay. We have silica and alumina layers, and in between layers we have sodium. And when this clay it's find some water, sodium has hydrophilic. He is love water. He absorb too much water and make and hydration. It's hydrated to bigger diameter, and this will increase the distance between layers and will be this will defined as clay swelling. So potassium or ammonium will enter the clay between clay layers and replacing the sodium and fit the space between layers. But this depends on the concentration of cations. We need we know in the sodium also it's active, it's a reactive it's reactive as potassium, but the potassium is more reactive than sodium. So if potassium is has sufficiently high concentration, we can replace the sodium. Here we have ionic diameters of the ion. We see here the sodium is just before the hydration is 1.96 angstrom, and after hydration it's 11.2. You see the hydration is too much, from 1.96 to 11.2. This is after hydration. But in potassium it's just 2.66, and after hydration is only 7.6. And ammonium also 2.86, and after hydration, same as potassium. And when we see this hydrated diameter here, we will find the potassium and ammonium is a very less values here. That's why we cause in hydration diameter is very less comparing with the others. This is in ionic inhibition. So potassium, it's ammonium now is not used too much. It's just rarely used. It's we used mostly we use potassium, KCl. We use KCl. We need the potassium to provide this ionic inhibition to replace the sodium and fit the space, because the space between layers is just only 2.8. So sodium is 1.96. We have space to let more water enter, but it's just very little space for water to enter. And after some water enter, it's the potassium, it's hydrated just to 7.6. It's not too much as sodium or as magnesium or calcium. Dehydration, osmosis, is caused by the imbalance of salt concentration between the mud water phase and the pure water. The salinity imbalance is separated by shale, which acts as a semi-permeable membrane that allows the transport of water only. So this osmotic is just transport water only, and water moves from low salinity to high salinity, from low salinity to high salinity, until the salinity difference it's balanced. If mud salinity is too low, so water will move into the shale, increasing the pore pressure. As pore pressure increases, it has adverse effect on stability. This will be swelling here. And if the mud salinity is too high, so pure water flows into the mud system, and this will be dehydrating of shale. So if salinity is too low, this will make swelling. If salinity is too high, this will make dehydration. We need dehydration. So that's why we make some salinity in our mud. And salinity in our mud depends on salinity of pure of fluids or pure water. Encapsulation is a chemical and physical interaction with the clay surface. Long-chain polymers such as BHBA is a partially hydrolyzed polyacrylamide. This is a BHBA. We abbreviation as a B from partially, H from hydrolyzed, and B from poly, and A from acrylamide, BHBA. Long-chain polymers such as BHBA and modified carboxymethyl cellulose. These are believed to wrap around the particles. How to wrap around the particles is ionic charge of BHBA negative attached to positive charge on the clay set, and this making encapsulation and coating to shale with a film. So this is one of mechanism, physically and chemically. Chemically by attraction from anionic charges and positive charges, and physically by this is capsulating by long chain polymers. Coating, or also it's a type of encapsulating or encapsulation. This is for glycol mode. It's glycol need two things: need downhole temperature, need temperature, and need salinity, specified salinity. Every glycol has a specified salinity with temperature to convert from soluble glycol to insoluble, and this make microemulsion or cloud point. So the glycol will convert from soluble to insoluble when find uh, specified salinity depends on the type of glycol and temperature. And because in bottom hole temperature, when we are drilling, we are not controlling the temperature. This is come from formation. We cannot change it, but we can change the salinity to reach the cloud point. So we can play on salinity or salt concentration to reach the cloud point, and this is cloud point will make as a coating and prevent water going to the shale and prevent swelling. This will provide inhibition, and we said here there are wide range of salinity of glycols, such as low salinity glycol or medium salinity glycol or high salinity glycol. You will find in the drums this is medium salinity or low salinity or high salinity, so you will range the salinity for this glycol. For physical plugging, we have silicate and silicate, soluble silicate. When find low pH shale or calcium and magnesium on the shale, calcium and magnesium ions on the shale, is immediately this soluble silicate precipitate as semi-insoluble silica film and make membrane, and physical plugging prevent more no more water will go inside the formation to cause swelling. So the silicate just when he find low pH of shale in formation and calcium and magnesium ions on shale, this is will immediately the soluble silicate will precipitate as a semi-insoluble silica film. Polyamine, he provide another type of physical plugging. It's electrostatic attraction between ammonium ion and anionic charges on clay. This is make neutralizing to negative charge on the clay and lead to physical plugging. And this physical plugging also reduce the water phase because no more water phase going inside the formation. So this will also provide inhibition. So here we have, this is the inhibition mechanism. It's the physical plugging for silicate and polyamine and coating glycol. It's encapsulation BHBA and dehydration. This is with salt, normal salt and ACL. Ionic inhibition. This is with KCl or ammonium chloride. We can use all most of inhibition mechanism together. So we can have MOT, for example, KCl to provide ionic inhibition and use it with silicate to provide physical plugging, or use it KCl with BHBA or KCl with glycol, or use polyamine and BHBA and glycol together. And also we can use salt here with the BHBA, with the glycol, or salt with BHBA and polyamine. So this is the type of mechanism, depends on reactivity of formation. Contamination, this is for inhibition. Contaminations, in general, a contaminant is any material that causes undesirable changes in drilling fluids properties. We said undesirable because we added in the mud, but in that time we this is material causes desirable changes. We need the change. We add some chemical to our mud to change our mud properties or enhance our mud properties. But contaminants, we talking about any material can cause undesirable change in the drilling fluids properties. So solids are by far the most prevalent contaminant. The first enemy for the mud engineer is the solids or drill solids. Some contaminants can be predicted and a treatment start in advance. These predictable contaminants are cement or makeup water, and sometimes salt or gypsum and acid gases such as H2S or CO2. But cement and makeup water, this is uh, we know before we drilling cement, we know we will get the cement contamination. So we can pre-treatment or makeup water also before mixing. We know this is our makeup water has some hardness, some calcium, some magnesium. So we will treat it before, then add another uh, chemicals to mix our mud. Other contaminants may be unexpected and unpredictable because this is will come while drilling. This table here, we have all contaminants or most of contaminants and the source of contaminants and treatments. Solids, the source of the solids, sure, the drill solids from the formation while drilling. And also it's a chemical. We have sometimes it's a commercial solids, barite or bentonite. If we add too much chemicals or we have high mud weight or like this, barite will provide this solids. So, but we are talking here mainly about the drill solids because for barite or bentonite is no issue. This is this barite is considered a high gravity solids, is no issue in our mud. We our problem in for low gravity solids in drill solids. Drill solids, here the treatment, it's dilution by fresh mud or uh, mechanical removal by solid control equipment, dump and dilution or removal chemical, mechanical removal. So this is the drill solids. No way to treat it chemically. You have to treat it by dilution, by fresh mud, or mechanical removal by solid control equipment. Is a shell shaker or desilter and desanter, mud cleaners, and centrifuge. Carbonates, it's a mainly is a CO2 source of CO2. Sometimes we find CO2 as a gases in formation, or sometimes it's a thermal or bacterial degradation of mud products. It's make or uh, make this CO2 sometimes we have air from mud hoover or shell shaker screen or hydrocyclones, and the be as a CO2, but usually CO2 from formation or bacterial degradation of mud products. Okay, if we have CO2, so we have, or carbonate contamination, uh, we have to treat it by lime. It's gypsum is not, this is rarely treatment. Is the common treatment is the lime for carbonate contamination. Anhydride, this is come from formation drills. We have formation is anhydride formation, or sometimes if we treat our carbonate with the gypsum, over treatment of carbonate problems with the gypsum maybe give will bring uh, gypsum contamination for you. So we treat the carbonate by gypsum, so we will treat gypsum by carbonate. It's work versus together. So treated by soda ash or sodium bicarbonate. Salt water or salt, this is formation drill. If we drill the salt dome or this is here, no way to treat the salt. If we have to drill the salt dome or salt formation, we have to convert our mud to salt saturated mud. But if we have just water, saline water from formation, so here just we had to dilute our mud with the water to go to the program salinity as we need it. Cement or lime, the source of cement operation. That's why after each drilling of out cement, we have cement contamination and treated by soda ash or sodium bicarbonate or citric acid. But common it's we treat it by sodium bicarbonate. So and also lime, if we have lime from formation or over treatment, so we will treat it by soda ash or sodium bicarbonate. Hydrogen sulfide, H2S, it's come from formation drills or thermal degradation of products, also bacterial degradation of products. If sometimes if our product is got some degradation, this will release some H2S. So we will treatment pH or precipitate by zinc carbonate. Here, mud engineer, when he make the test for full test, the usual full test for parameter, when he find the increase in plastic viscosity and slight increase in the gel and YB and fluid loss, and also increase in solids and MBT, slight increase here. So this he has solids, especially if BV increased very high. Here we have contamination of solids. This table is very important to determine which contaminant you have after you do the test. Cement will increase the funnel viscosity, will slightly increase the BV, will increase the YB, increase the gel, increase the pH, sure, because the cement slightly increase the fluid loss, increase the BF and MF, alkalinity of the mud, increase the Bm, slightly increase the calcium. This will be cement contamination. Gypsum will increase the final viscosity. Here, same as cement, but the difference here in pH will make drop in pH because gypsum is the acidic formation. Here, the pH will be high in cement, in gypsum, pH will be down. So, and fluid loss will get higher, and BF and MF also is not like cement, it will be down, and BM also, because this is a mud alkalinity, all will be down, and calcium will be very higher because the gypsum will release the calcium. So here we have gypsum or anhydride contamination. Salt will increase your viscosity, will increase slightly your BV, will increase your gel and YB, you drop pH, increase the fluid loss, and drop alkalinity, and increase the chloride. If you increase the chloride, that means salt is no other contaminant will increase your chloride. It's just only the salt contaminant will increase the chloride. So if you find the chloride is very high, that's where you have, that means you have the salt contaminant. Temperature, if you high you formation is very high temperature while drilling, it in bottom hole temperature is very high, so your rheology will get higher because your mud will flocculate it, because you will lose the water by evaporation from the mud. So your viscosity and YB and gels will be very high, and also the pH will be down, fluid loss will be high, and alkalinity will be down, slightly increase in BM. This is, we have high temperature. High temperature we treated by using some stabilizer for temperature to stabilize the polymer to work here okay, because fluid loss here is be higher. You need to stabilize the polymer to provide same range of filtration. And also we can use mud cooler. This is as centrifuge, and like this is you can mud going inside the mud cooler, through the mud cooler, and come back again to the tank with after cooling. So, or also we can use the high temperature chemical products. For example, in fluid loss, here if we find this situation and we use for fluid loss as a starch, we have to replace the starch with the bag or dress bag to provide high temperature filtration. Carbonates also will increase our viscosity and increase our BF and MF, but will not increase the BM, will not change the pH. So this will be carbonate contamination. From BF and MF, we can know the it's carbonate or bicarbonate, depends on the values of BF and MF. So after find, we know the contamination, the source of contamination, and how to treat, and how to determine which contaminant we have. So here the factors to treat. For example, if we have calcium and increase and measure our calcium, we find our calcium in the mud is 1000 milligram per liter. So we want to treat, this is 1000 milligram per liter of calcium. We treat it by soda ash. We multiply the concentration of calcium in this factor. It's point 0093 multiply 1000 milligram of liter calcium, and this is will give us pound of barrel of soda ash, and after that we can uh, know how many sack of soda ash needed as per your mud volume you have. For sodium bicarbonate, it's point uh, 0074. Here this, because this is for 100 milligram per liter, and when I say this is 0074, I mean for 1 milligram per liter. So carbonate, if we need to treat by gypsum, it's 0.018 for 100 milligram per liter. For lime, it's 0.043 for 100 milligram per liter. Bicarbonate, it's also same factor of lime. Sulfide, zinc carbonate, 0.140, or zinc oxide 0.106. So we have to know these factors to determine the quantity of treating agent to treat the contaminant when we uh, face it. We have also contamination due to bacteria. So the presence of bacteria in a drilling fluid does not in itself present a problem. Bacteria in itself is not a problem for our drilling fluids. But there are two general situations where bacteria may become problematic. So aerobic bacteria can cause degradation of organic viscosifiers and filtrate loss reducers. This situation is more likely to occur following long periods of non-circulation. So long stoppage of circulation, non-circulation, for example, logging for 3-4 days, or stop operation for anything regarding logistic, or regarding any security or any issue, we stop our operation for long days. In that time, our mud, maybe our viscosifier or fluid loss controller will be degradable, and make some bacteria here, and we find our parameter is not as before, because is some of viscosifier or filtrate loss reducer is not working more. And also here, that's why before logging operation, or before run casing, before pull out the hole for long time or like this, we put our biocide in our mud to prevent the bacteria. Anaerobic bacteria may reduce also sulfate ions. This is another scenario or another situation to make our bacteria's problematic uh, issue. This is reduce the sulfate ions to sulfite ions, which combines with the hydrogen to form hydrogen sulfide. It's sulfite ions with hydrogen to form H2S. Here will be very risky. Our bacteria can make H2S, and H2S, it's a contaminant and also is a danger gas. So H2S cause the fluid to become corrosive, and again this is the situation more likely to occur following long periods of non-circulation. So the best method for prevention of bacterial problems is to treat it, the makeup water or with biocide, and maintain adequate levels of biocide in our drilling fluids. It's from time to time we have to add some biocide to our mud in case of the stop circulation for a long time. It's non our mud will not our chemical will not be degradable, and or our this sulfate we cannot change it to sulfide and become H2S. So our contamination due to bacteria is just easy way to prevent. It's just use biocide in your mud. Here we reach the final of this course, and for this session and for this course was 4 sessions, and I wish this course was beneficial and useful for you, and we can open now for question and answers.
Thank you, Mr. Ghassan. Now we will pop out to the question and on to the question. Let us see what kind of question we have today. Okay, I'm looking for a question, but sound like there is no question actually. There is someone asked about. He said that he have a question related to the clay types and their response to the replacement between Na and K. He want to elaborate in this point. What is the relation between and the response between the clay types and replacement of N, sodium and potassium?
Okay, it's this is this is replacement between potassium and sodium. Yes, actually it depends on the type of clay. It's we have some clay as such as montremonite. This is has sodium inside between the layers. So in this type of clay, we use the KCl to replace the sodium with potassium. But we have, for example, a light. This is type of clay. This is a light has no sodium, so this is will not consider as reactive clay. So we have some shells. We drill some shells is not uh, reactive. No need to drill with KCl or inhibitive mode because no sodium inside and inside the layers. So no more ability to hydrations because we said the sodium is a hydrophilic. It's a like the water. When he find water, he absorb too much water, and this is make hydration for clay. If the clay has no sodium inside, so we not find that this is level of hydration, so no need to use the KSL or inhibitive mud to drill this clay or this shell.
Okay, there is another question about slides.
Mhm.
He said we should get them, I guess, ASAP.
Yeah, inshallah.
Uh,
All slides and videos, inshallah, will be soon ready.
I think slides in the well, I guess. Slides in the well.
What?
Slides, a slide in the well. He is asking about the slides, not the slides. I don't know how to say it, but
Hmm.
his question. I just will read the question as it has been written here. He is asking about Okay, let me check it out again. I'm looking for the question. Okay, we'll go to another question. Until I find it, I will repeat it for you.
Okay.
Okay. The question said, if I got your point, that you mean we must add biocide after WOC and after wireline logging before resume drilling.
Not after wireline. Before, when we are want to pull out of hole for wireline logging. So we know in that time we will stop circulation for 3 days for wireline. So in last circulation before wireline, we add the biocide to our mud to ensure our mud inside the hole has some concentration of biocide to prevent bacteria degradation. So we will add biocide in last circulation before pull out of hole, before wireline operation, before ram casing, or before uh, uh, non-stoppage. If we know we want to stop the operation for 3 days or 4 days waiting on the tool or anything, in the last circulation, we have to add our biocide to our mud and keep this is biocide circulating. And when we finish circulating, this is in that time we will ensure our mud he has enough concentration of biocide, and this will prevent bacteria degradation for 3 or 4 days. And when again we uh, resume circulation, we will find our parameters is okay.
Okay. For that question, Mr. Ghassan, he asked about the slide. Actually, I think about the slide and the well, maybe because we are talking about the
Okay.
clay, because we are talking about the clay, and so I guess that he is talking about the slides on the well, but he actually asking about the
You
slides
mean
for the
sliding
exam.
is a deviation well or deviated well?
Okay, but he asking about the slides for the exam actually. So
Okay. Okay.
okay, okay. Okay. Uh, Now, only half of the truth that I've been here, but a great help provided by all the BNA team. So I want to thank everybody in the BNA team. Thank you for you, Mr. Ghassan, for this enlightful, useful, informative, illuminating series of lectures through this first course. Also, a big and great thanks to everyone. We cherish that you were being here with us. I just want to remind everybody that all session will be uploaded. Then the time of the exam you will be informed, inshallah, so soon. So keep in touch on the BNA website or LinkedIn or whatever to know the exact time of the exam, inshallah. So goodbye for everybody, and stay safe, and goodbye again. السلام عليكم.
وعليكم السلام.